Okay, we're going to review for the exam this afternoon, but I am also, as I told you, going to work out problem 5 for the homework set. Now, the homework was supposed to be due now, but obviously you can't turn it in now because I haven't gone over homework 5. So I will give you, let's say, turn in next, let's say, Tuesday. Just, that way you don't have to say like, oh, I got to get this done, got the test, got other things for the test. So problem number 5 has the differential form of Gauss's law. Now, I know I can pull it up, but I'm just going to borrow yours again. Well, I'm going to read the problem here to make sure I don't mess something up in the problem. The problem says, given this electric field is the average electrostatic field in the Earth's atmosphere in fair weather, where A, B, alpha, and beta are positive constants. So we have 4 positive constants in there. And Z is the height above the locally flat surface. So we're treating the Earth as a flat Earth here. Obviously it's not, but on a reasonably small scale, that makes sense. Find the average charge density in the atmosphere as a function of height. What is its sign? Overland typical value is around 250 newtons per coulomb. So let's look at that equation first. What direction is the electric field pointing from the Earth? In or out?
Does it say it's positively charged?
Well, that's the thing we're going to determine from this. So is the electric field pointing in or out of the Earth? Z is out of the Earth, so is it point in or out?
Because it's negative.
Because it's negative, the Z direction is pointing in. So the electric field is pointing into the Earth. What does that tell you about the charge of the Earth? It's negative. Now, this in itself is somewhat controversial. How can the Earth have a negative charge? Shouldn't it be neutral? Would that make sense? And so some people believe that there must be, like a conducting region in the shield, or, somehow you have charge neutrality, because it doesn't seem to make sense that the Earth wouldn't be neutral. But looking at that electric field, it would seem to say that the Earth has a negative charge because the electric field lines are going into the Earth. So we have that already. Now we want to find the charge density of the Earth. So, or actually the charge density, let's just go for it. So we use this equation that's at the top of the page. This is Gauss's law in its differential form. What we've been working with for most of your homework is Gauss's law in the integral form. So Q enclosed, since density multiplied by dV and integrated up gives us Q enclosed, you can see that there's a relationship between rho and Q enclosed. That's an integral relationship to go from density to Q enclosed, or a differential relationship to go from Q enclosed to rho. So we can see how this would be probably a similar thing. But then we have the confusion of this thing here, that gradient operator. I believe I introduced the gradient operator at the beginning of first semester when we did our math stuff and said this is going to be coming up. And I don't think we've used it since then. But here's where we definitely are going to use it. So the gradient is a directional derivative. Here is, notice it's an upside down delta with a vector sign above it. And that means that in the x direction it's ddx, in the y direction it's ddy, in the z direction it's ddz. When you see it written out that way, it's pretty clear why we call it a directional derivative. This is something that Chad is going to be becoming very familiar with in its 3-dimensional spherical coordinates form, which is much harder, believe me. So it's the directional derivative. So what we need to do is we just need to do the dot product of this directional derivative with this function. Now notice, since it's a dot product, we're going to have del dot E is equal to d dx times, or acting on EX, plus d dy acting on EY, plus d dz acting on EZ, where EX, EY, and EZ are the X component, Y component, and Z component respectively of the electric field. Now in this problem, he made life easy for you. Because what is EX? How much electric field do we have in the X direction?
If, like you say, here, this
In this equation. In this equation. That's right, Chad. There's nothing. How much in the Y direction? Nothing. It's all in the Z direction. So right off the bat, because this is all in the Z direction, I can say, well, this is 0, and this is 0, and I only have to do that derivative. Furthermore, the only variable in there was dz. So even if there was an X and a Y component, if they only depended on Z, it would still not matter. Okay, so let's do that derivative. So there's writing out the derivative I'm going to do. I haven't done any math yet, just wrote it out. Well, I did apply the dot product. So doing the derivative, E0 is a constant, so I can bring it out. Then I'm going to have derivative of an exponential. A is a constant, so I wrote it down. Derivative of an exponential, you just take the derivative of the exponent and bring that out front, and then you have the exponential. So the derivative of e to the minus alpha z is minus alpha e to the minus alpha z. And likewise, derivative of e to the minus beta z is minus beta e to the minus beta z. Notice I have a minus out front. I changed color to make this clear. I have a minus out front, and then I have a minus in each term. So everything's going to turn out to be positive. So I've calculated del dot E, and according to the differential form of Gauss's law, that's equal to rho over epsilon 0. So I'm one step away from my final answer. What is the charge density in the atmosphere according to this law? To make sure we're following along, everyone write it down. Chad, you can write it here because you don't have paper out. Chad's all, I can get paper out. Oh, I can give you a piece of paper. just having you guys do it to make sure you're following along and not lost. My wife likes to say lost in the sauce, which as far as I interpret means drunk. Well, you start this. You start this stuff. That's definitely this. Yeah, this was. These were questions. That's exactly. So just cross multiplying, we have epsilon 0 times E0 times A alpha e to the minus alpha z plus B beta e to the minus beta z. So we have a positive charge density in the atmosphere, a negative charge in the Earth, and a positive charge density in the atmosphere. That makes some sense, right? That makes some sense because, well, that's why we have a negative here, is because we have a positive out there. Okay, now we have a couple more questions, I believe, to go with this. Well, first one is plot the electric field as a function of elevation. That's just graph this function. So what do? Well, e to the minus alpha z and e to the minus beta z. Because we don't know what the constants are, we can't get an accurate number or graph, but what we can get is a shape. And that shape is going to be, I totally ran out of space, so it's going to be a small graph. Where's my, here we go. It's going to be a small graph right here. So it was negative, so I actually should put my axis up here. And this is going to be the electric field. And this is going to be the elevation z. And because they're exponentials with a negative power, they're getting closer to 0 as you get to larger. And so it's going to be something like this. And that's as close as you can come without knowing what the numbers are. I mean, there are different variations on the shape depending on what A, alpha, B, and beta are. But it's going to have to look something like that. Then we had describe how you plan to solve the problem. What concept is involved? Okay, so this one here, I've told you numerous times, we're going to have to use the differential form of Gauss's law for this. So that's the concept involved. Which equation will you use to y? The equation of Gauss's law. So, and then the equation of the differential form thereof. And why are we going to use it? Well, because that's what actually allows us to go from electric field to charge density. The integral form allows us to go from charge density to electric field. So that's right. If you're trying to find the electric field from the charge density, use the integral form. Then here we're going the other way. Instead of solve the charge density, sketch the charge density as a function of z. Is it positive or negative? So sketching the charge density, so now I'm going to go down to the bottom. The charge density as a function of z. The charge density was positive, E epsilon, and then those exponential terms. So the charge density is going like this with an exponential decay. And once again, without knowing the different constants, you can't put in the actual numbers. So that is the end of that problem. Now, is the problem tough? Chad says, yes, it was tough. My graphs are beautiful things there. So, yeah. It wasn't very many lines. We only had to do one derivative and then multiply by epsilon 0. So compared to the other problems in this assignment, this was super easy, which is what I said. This was super easy. We'll do it in class. But still, it's not trivial, right? You did have to do a derivative. You had to do some work with it. So the point of this is to see the Gauss's law works in both ways as an integral equation and a differential equation.
So this is just one of the instances that you need to do.
Right.
Just because of the relation.
Because we're trying to find the charge density. Right? If we're trying to find the charge density, the differential equation is the one we're going to use. And actually, when we get to deriving electromagnetic, the equations for electromagnetic laws, for Maxwell's equations, we will go through and use the differential forms then as well. Okay, preparing for the test now. So you have one calculus-based problem. And all of the homework that you've been working on, and Michael, you haven't come for help with homework, which has me worried, because this is hard homework. It's not easy homework. And doing it on your own is possible, I suppose, but we are just learning these things, so it's not probable. So I encourage you to come if you have questions. So how do we choose if we're going to use Gauss's law or Coulomb's law? Well, first of all, Gauss's law and Coulomb's law are fundamentally the same. Coulomb's law is easily derived from Gauss's law. So let's just quickly, what are Coulomb's law and Gauss's law to make sure we understand that. So Coulomb's law. There's Coulomb's law. The electric field, now I put it in the electric field form rather than the force form like it was first introduced. The electric field for a point charge is kq over r squared r half. Now, of course, we have the differential form of that where dE is equal to k dq over r squared r half. But that's Coulomb's law. And what is Gauss's law? Gauss's law is that the electric flux from a closed surface is equal to the charge enclosed over epsilon 0. So those are the two laws, and when you look at them, you're probably, I don't see the relation, right? But it's actually really simple, because Coulomb's law, as stated, is for a point charge. All we have to do is take a point charge and apply Gauss's law to it. So here's a point charge. What kind of symmetry do I have for that point charge? Spherical symmetry. That's the first question you ask. You look up here, if the charge distribution has exploitable symmetry, e.g. spherical symmetry, cylindrical symmetry, or infinite planar symmetry, I realized this morning when I was talking to Chad that I should just call that mirror symmetry, right? Because that's what infinite planar symmetry is a mirror symmetry. Then Gauss's law is almost certainly easier. And in that case, then we say we have an exploitable symmetry and where do I have it? Okay, I don't have it right here, so I won't. And then we want to choose a shape where it's going to be easy to do the calculus. And so the calculus is the electric flux is the integral of E dot dA. What does the circle on the integral sign mean? It's a closed surface. There's no holes in it. So I have to have, if I have my charge here, I have to have, let's say, a box around it with no holes in the box. And I'm calculating the flux on each side of the box. I could do that, but it would be hard. Go ahead.
How about if like two spheres are?
Oh, you like the last problem, maybe?
Yeah, it was.
Okay, so for that last problem, treat each sphere as if it's isolated in a complete sphere. And then you find the equation for the electric field, and then you're only looking at the region of overlap. So you use the equation for the electric field inside the sphere and the region of overlap. So you have to then draw your coordinate system and find where the overlap is and go from there. But you use Gauss's law on each sphere like it's isolated. And then just remember, you can add electric field vectors. So we just have the electric field from this one and the electric field vector from this one. Okay, so back to this. I could make a cube that has no holes in it and I could use Gauss's law. But it would be kind of rough because the angles are constantly changing. So that E dot dA would have an angle term in it, and the electric field is going to be changing with distance. So that would be kind of rough. But if I can choose a shape that is going to have a constant electric field over the surface and a constant angle between the electric field and the area for the surface, then my life becomes easy. With the spherical symmetry, the only thing that can change the electric field is the distance from the center. So I want to choose a surface.
That means you can choose any part of the particular part.
Any particular what?
And you can choose any particular part on the sphere.
Well, we integrate over the entire surface. So in the end, I'm doing the entire surface, not a part of it.
Yeah, but I mean you start.
Yeah, I draw my picture for just this piece. So I need to have a constant radius so the electric field isn't going to change on my surface. And immediately a constant radius from a dot is a sphere. So that tells me my calculation is going to be simplest if I choose a spherical surface for doing the calculation. And that choosing of surface is oh so important. So I choose a spherical Gaussian surface. Now to reiterate, the Gaussian surface isn't an actual surface that exists. It is a shape that I am making up in my mind for doing a calculation on. And it's spherical because of the symmetry of the electric field. So on the spherical Gaussian surface, I'm going to have E is parallel to dA everywhere on the surface, and E, magnitude, so I drop the vector sign, is constant everywhere on that surface. I'm going to change color just for that. So that makes my integral easy. Because if E is parallel to dA, then E dot dA, since dot products are multiplying the parallel parts, is just going to be equal to E times dA. And if E is constant, the integral of E dA is going to be E times the integral of dA, which is just EA. And as Nathan said, we might have to say pay royalties if we say that too many times. So the flux calculation turns out to be trivial because of the appropriate choice of Gaussian surface. If you'd chosen a cylindrical Gaussian surface here, it would be non-trivial because you would have the electric field, once again, changing angles and changing strength on the side of the cylinder. You could still technically do it, it would just be a lot more work. So here we have our flux EA, and then we have to say, okay, it's a sphere. The equation for the area of a sphere is area is equal to 4 pi r squared. So the flux is equal to E 4 pi r squared. Now Gauss's law says that's equal to the charge enclosed over epsilon 0. In this case, I just had a single point charge. The only calculus we've been doing in these Gauss's law problems is the calculus of integrating up to find what the charge enclosed is. In this case, there's no need to integrate because it's a point charge. And so I'm just going to have Q enclosed is equal to Q. So I replace Q enclosed with Q. And now I solve for E. Now, this is scalar. I started with Coulomb's law as a vector. What direction is the electric field pointing? It's coming out. So I can now add the vector portion. I had that inherent to my work here when I was talking about the direction. So it's not like I'm making it up and adding it in later. I had it in my calculation that the electric field direction is pointing out. Because I said for a spherical distribution, the electric fields have to be radial, right? They can't be anything else. So because, well, when we talk about Ampere's law, we'll get a better handle on that because Ampere's law is different. The reason Ampere's law is different because magnetic fields always do loops, whereas electric fields go out of positive into negative. So if it's going out of positive, the only option is radial out or radial in. And out of positive is radial out. So we had that identified. I didn't say them, but when we did this. Now, how is this equation in the black box different than the equation in the blue box? Yeah, the blue one versus the black one. Yeah. But K is defined as 1 over 4 pi epsilon 0. So, So yes. So you have down here, if you replace 1 over 4 pi epsilon 0 with K on top, then you have KQ over R squared. So there you see, through a fairly short derivation, that Coulomb's law is Gauss's law. It's Gauss's law for a special situation of a point charge. So whether we use Coulomb's law or Gauss's law, it's the same fundamental underlying law. Part of the work that James Clerk Maxwell did in coming up with his equations was realizing that they had lots and lots of equations, and he collapsed them down by saying, well, this equation is just a special case of that equation. And this equation, and coming down saying, these are the fundamental ones. So back to test prep. You want to look at your symmetry. If you have some kind of exploitable symmetry, cylindrical symmetry, spherical symmetry, or that mirror symmetry of problem 7, then Gauss's law is going to be the easy way to go. Because you basically won't be doing calculus except for maybe the part about determining how much charge is enclosed. If you don't have a simple symmetry like that, it's probably going to be easier to use Coulomb's law. So here's Coulomb's law in the differential form. The electric field created by a point charge is KQ over R squared. So if I have a charge, now the field due to some tiny dq, we'll call the electric field due to dq dE. So dE is equal to K dq over R squared. And you still do have the vector vector aspect, but I recommend that you work the problem as break it into X components, Y components, and do each component separately, rather than trying to deal with a full-scale vector problem. So that's what we did, for instance, in problem 1B in the homework. We did the Z direction and the X direction as 2 separate calculations. So now, in applying Coulomb's law, we have 3 different fundamental ways we can have charge distributed. We can have charge distributed on the line. We can have the charge distributed on the line, in which case we say dq is lambda, the charge per unit length, times ds, which is the piece of length. I use ds here because it doesn't have to be in the x direction or the y direction or the z direction. You can have a curving line of charge, and you can still do it.
It doesn't matter the shape, it's just
It doesn't matter the shape for the equation here. For the application, for doing the math, it matters. Right, because the shape, different shapes will be harder and easier. And so the first one we did, it was a wire that was going in a circle, and that kept the radius constant, made our life real easy. And then we went to ones that were harder after that. And then the hardest would be if you had, the wire doing some kind of random motion, then it would be really hard. Second variation, if you have the charge spread out over a surface. Charge spread out surface, like if you have a conductor. All the problems we had in our homework were insulators. Because insulators, you can have charge density. If it's conductor, the charge is all on the surface. And so we had insulators with charge spread out throughout them, which means you have electric fields throughout them as well. And so then you have dq is equal to the areal charge density, charge per unit area, times dA. And dA in Cartesian coordinates, that'd be dx dy. In other coordinate systems, it gets a little more complicated. I don't think we did any aerial problems. And then we have the three-dimensional case, which is the dominant case, where charge is spread out over a volume. And then you have dq is rho dV, where rho is the charge per unit volume. And as we saw in our homework assignments, we had rho doesn't always have to be a constant. It was a constant for the last one, and numbers 5 and 6, or 6 and 7, it was constant. But for the others, it wasn't. And so we had to go through and calculate the charge enclosed. Yeah.
So what do you mean by charge spread over volume? Internally or on the exterior?
Internally. It's spread throughout the material. Okay. And then notice the use geometry, break the components, and solve each component independently. It's going to make your life easier. Gauss's law. So that's a review of Coulomb's law. Gauss's law, I did an example of Gauss's law already, but that's the one that is conceptually, I think, more difficult. Even though it's easy to state, right? Gauss says, you tell me how much electric field is coming out of this region, I'll tell you how much charge is enclosed. That's all Gauss's law is. If it's more charge enclosed, there's going to be more electric field lines coming out. And how do we calculate those electric field lines coming out? That's where the term electric flux comes in. The flux is the calculation of how much electric field is coming through a surface. And so that flux, the integral of E dot dA, is fundamental to Gauss's law because that's the part of Gauss's law that's telling me how much electric field is coming out of the region. Because it's how much electric field is coming out of the region, you have to have it closed. You can't have any gaps. You can't say, oh, well, there's some electric field going through this part, but we didn't worry about that. We just did the rest. Well, then you're missing part of it. And who knows, you might be missing something really important or it might be trivial. So you have to have a closed surface. So when you're using it, always identify any symmetry you have to determine if Gauss's law is going to be the way to solve a problem. Now, it can be used outside of these symmetry problems. For instance, well, here's a real simple problem that you definitely won't see. We have a cube, and let's say each surface of the cube has the same flux of 3, what are the units for flux? Electric field times area, right? So electric field is newtons per coulomb, area is meters squared. So that would be our unit for electric flux. Magnetic flux, we actually have a name for the magnetic flux unit. We don't for the electric field, at least as far as I know. And so if each surface has that much flux coming out of it, how much charge is inside of that cube? Right, I took away the calculus by giving you the flux through a surface. That's why this is easy. How much charge is coming out of that, or how much charge is contained in that cube if you have that much flux through each surface?
You just multiply that by surfaces.
Okay, multiply that by 6 because you have 6 surfaces and that's the total flux. So you'd have the flux total and according to Gauss's law, that's equal to the charge enclosed over epsilon 0. And so the charge enclosed is 6 newtons per coulomb times meter squared times epsilon 0, 8.85 times 10 to the minus 12 coulomb squared per newton meter squared. And you'll end up with a charge that, is a number, 6 times 8.8. Let's say 6 times 9 is 54. So it's almost 54 times 10 to the minus 12, or 5.4 times 10 to the minus 11 coulombs. That's a rather trivial case, but it shows you it doesn't have to have the symmetry. You could have gone the other way. You could have said, if I have a charge of 10 microcoulombs, well, let's make life easy, 6 microcoulombs enclosed by the cube, how much flux comes out of each surface? That would just be going the other direction. And then, worst case scenario is, you have a function for the electric field, and you calculate the flux, then you have to do the dot products and do the integrals. That gets harder. We're not going to do that simply because I want you to understand what Gauss's law is and how to use it. Worry about calculus in your calculus development in calculus class. You have to admit the calculus we're doing is hard enough as it is, right? Okay, applying it. You want to identify surfaces on, right? You have to choose a Gaussian surface, the surface that you're going to do your mental calculations on. Not a real surface. What are you doing calculations on? So that you can determine the relationship between the charge enclosed and electric field. So you want to choose a surface that has the electric field points in the plane of the surface, so flux is 0. That would be the case of E dot dA equals 0. So an example of that would be, here's my surface. So dA goes that direction. And if the electric field is going that direction, then E dot dA is 0. If you can make your surfaces so that's the case on, that's the case on all of the surfaces, you have a flux of 0, no charge enclosed. But if you can have all your surfaces that fit one of these, it's going to be easy to do the math. The second one, electric field, has a constant angle with the surface and is constant on the surface. So that's the case that we were looking at, where we had surfaces like this. So dA is like this, and then we had the electric field pointing radially. They're parallel, so the angle between them is always 0 degrees, hence the dot product is just E times dA. And because for the spherical symmetry that we've been doing, only the radius matters for the strength of the electric field on the surface of the sphere that's centered on the charge distribution, that's always important, then you're going to have the easy flux is just electric field times the area. I think I have another one here that talks about specific cases. No, I don't. Okay, so specific cases, come on, go back. If you have a spherical charge distribution, which could be anything from a point charge to a sphere with charge varying throughout, as long as the function of the charge variation only depends on R, then your Gaussian surface should be a sphere. And if you want to find the electric field inside, you're going to have the radius of the sphere inside, and the amount of charge enclosed is going to change with the radius. If you want to find the electric field outside, then the radius, of course, is bigger than the radius of the sphere, and the charge enclosed is a constant. So you have two different regimes there. If you have a cylindrical distribution, the example we did in class of the cylindrical distribution was the infinite wire. Infinite wire is going to look the same in all angles like that. So that angle can't make any difference. Only the distance away can make a difference. It also, if it's infinite wire, it doesn't matter what your elevation is, it looks the same.
What did they say to that? Okay. What if the wire is not?
If it's not infinite, that's going to break your symmetry. Because if it's not infinite, you're going, well, like you had in problem one. Problem one was not infinite. And when you were above the wire, you had an electric field that was pointing up. If it's an infinite wire, you're not going to have anything up because you have just as much charge above as you have below. And so the vertical parts are going to have the zero, and you're only going to have the horizontal. If there's an end, then you introduce the vertical part. So, right, it has to be infinitely long. Now, what if it's not infinitely long? If you are much closer to the wire than the distance from where you are to the end of the wire, you can treat it as if it's infinitely long. But if the distance you are from the wire is similar, like within a factor of 10 to the distance to the end of the wire, then you're going to see that break in symmetry and build. Now, when we did capacitors, in general physics class, we said the electric field between the plates was uniform, just going straight across. That's actually an application of problem 7. The last problem is a flat surface, and I know Chad finished it, and what you find is that you have a constant electric field above the flat surface. But that's only going to be true if it's an infinite plane. But if you're close enough to the surface that the edges are 100 times farther out than you are from the surface, then for all intents and purposes, it is an infinite surface and it's applicable. So for capacitors, we put the plates so much closer together than their length that for most of it, we can treat it as if it's an infinite surface and you get that electric field. So yeah, in short, the last problem is fundamentally the same calculations you do to find the electric field inside a capacitor. The only difference is in a capacitor, you have a conductor, so all the charge is just on the surface rather than throughout the metal. Let's talk about that last one just real quick. Oh, we got 2 minutes, maybe not. Okay, we can talk about it because I didn't go through this. I'll go through this when we talk about magnetic transient circuits. So the last problem, the last homework problem, you have an infinite plane. So here I'm just looking at it side on. The infinite plane, and the problem tells you that it's, go away, D and D. It's 2D is the width of that infinite slab. So I need coordinate system. I'll go ahead and define X is going down my dashed line through the center of the slab, and Z is vertical. Yeah, you only need 2. As I was telling Chad, yeah, you could put Y back here, but who cares? The XY plane is the plane of the slab. Z is coming out of the slab. So now I need to decide what kind of symmetry do I see here. And as I said earlier in the lecture, what I see is a mirror symmetry about the center. Right? Everything on the top half is exactly the same as on the bottom half, just mirrored. By the way, it tells you that it's a charge density rho. Presume, since it doesn't say negative, that it's just a positive charge density throughout. So if I have positive charge, what direction do electric field lines go with respect to charge? Come out. The lines are going to be coming out. Based on the symmetry, I have as much charge to the left as I have to the right. So electric field lines going horizontally are going to add up to 0 because I have a balance from both sides. So based on that symmetry, the electric field lines have to be going, and I'm going to go into the material here. The electric field lines have to be going like this. And based on the symmetry, like that. This has an exploitable symmetry, so we're going to use Gauss's law. I'm sure it's possible to do this with Coulomb's law. I've never tried it. But because it's easier with Gauss's law, I'm quite sure. So Gauss's law, the first thing I need to do after I define, I have an exploitable symmetry, is to determine what kind of shape I can use to exploit that symmetry. So notice I have the electric field lines, vertical. So if I can make all of my surfaces either vertical or horizontal, I'll be in pretty good shape. My horizontal surface, though, has to have a constant electric field. What's the only dimension that could change my electric field in this geometry?
Medium direction.
Yeah. Well, what's the only, well, we have X, Y, Z. What's the only dimension, like by changing X can change the electric field, by changing Y can change the electric field, by changing Z can change the electric field, based on our geometry? Only Z. So that means that I'm going to need to have a surface that is at constant height above my plane, so that I'll have constant E. So I'll make a surface here, and notice I made it circular. You can make it square, you can make it star-shaped, you can make it whatever you want, as long as that surface is such that dA is parallel to E. So it's at constant elevation, so as was pointed out by Michael, based on the symmetry, the electric field on the surface is constant and is parallel to the area. So on this surface here, I'm going to have the flux is equal to no circle because it's not on a complete closed surface now, it's just on this surface, equals EA. What's the area of that surface? Don't know, don't care. It's just A. Okay, then I have to choose another location. I want my other location to be easy. There are two easy spots for the other side of this object. One is at the center. Why at the center? Because symmetry dictates the electric field at the center of the slab is 0. The other is to go symmetrically below because symmetry dictates that it's exactly the same below as it is above. So I'm going to go, I'm going to go below. So down below I have, I see it's time to go. If you need to go, just get up and leave. So dA and electric field are parallel to each other. Since the electric field and dA are parallel to each other, I didn't draw an arrow for dA. Then I'm going to have the flux on this surface is exactly the same as on the top surface. Now what about the sides? What direction is the area on the sides? I made mine a cylinder. What direction is the area on the side of a cylinder? Area is always going out, so the area is like this. But what direction is the electric field pointing? Vertical. So that's a 9-degree angle between the dA and the electric field. So the flux on the side is 0. The reason I use the cylinder is because there's only one side. And so my total flux is equal to 2 times the electric field at height Z times the area. And now I have to say, now how much charge is enclosed by this surface? I have charge density rho that extends from Z equals minus D to Z equals plus D. No charge density outside of that. So in general, the charge enclosed is equal to the integral of dq, or equal to integral of rho dv. Since rho is constant, that's just going to be equals rho integral of dv, which is rho v. Well, what's the volume of the charged material here? Volume for a cylinder is the area of the base times the height of the cylinder. So that area is A. Once again, don't know, don't care, because it appears on both sides. It has to. If it doesn't, I made a huge error. And then what's the height where I have the charge here? Well, it's 2D because I'm going farther than the extent of my slab.
We just that area.
Yes, because there's no charge outside of there. And so then I have my charge enclosed is equal to rho times 2AD. So I've got the flux and I have the charge enclosed, but that's got to be equal to the charge enclosed over epsilon 0. So 2 rho AD over epsilon 0. Notice I have an area on both sides. Divide both sides by 2, and I'm done. My electric field strength is equal to rho d over epsilon 0. It's constant outside of the slab. What's different if I go inside of the slab? It's not 0 inside the slab because it's not a conductor. But if I go inside of the slab, then my volume is only going to be going up to plus and minus z. And so my volume will be A times 2z instead of A times 2d, which means I'm going to replace my d with a z in my final answer. All right, I have gone over time. I'll see you in an hour and a half, except for Chad, who I'll see in a half hour.